Hello, Tim Guttormson here at SoDak Labs, agronomist, RST, seed physiologist. Here today to talk a little bit about sweet corn testing at SoDak Labs. Have several tests to go over today, and then in the end we'll talk about developing an index for the sweet corn, specifically the SH2 sweet corns. Thank you. And at SoDak Lab here, we like using the sand test for sweet corn. And in the AOSA rules, it defines different methods. We use what's called the TCS method. It's the top of crepe cellulose paper. So the crepe cellulose paper is put on the tray and a standard amount of water is used. The seeds are planted, and we're mostly looking at SH2 sweet corn here today, and then it's covered with sand, and this is a river washed mason sand. So a little bit of variability in particle sizes, but in general pretty uniform medium. We like sand because it does a couple things. It allows uniform water uptake, which helps us see difference in seedling vigor. As you can see here in this first tray, we have some seedlings that are varying pretty uniform water uptake, you know, here, but you see some variability in seedlings. So strongs and slow. And so sand allows us to do that classification. And like on this lot here, we're saying 88% strong and 1% slow is the average. So anyway, we're looking at this at about 7 days after being planted. So this lot of sweet corn here, this specific one, when we look at it, you know, we see a decent 89% germination, and we do rate the presence of saprophytes. And here you can see a little mycelium growing on the sand, and that could be Rhizopus species or Mucor species, but it's considered a saprophyte, not a pathogen. It's really living off something leaking out of the seed, and likely sucrose. All right, so we're back. What we did is we moved our sand germ, warm germs to the back, and then we added our 50 Fahrenheit cold tests in front of them. So what we're doing in a cold test, we're doing 200 seeds, again on the TCS method. But the thing at SoDak is we make sure these seeds are definitely imbibing 50 Fahrenheit water. And, you know, when you take an overview here of this, there's sort of a wow effect here on these 5 lots. It's clear that this lot is responding the best to the cold test. And the other 4, not quite as well, for sure. So we'll talk about these a little bit. You know, you see, when we compare our strong lot here, and this has got an 80% tray cold, so 50 Fahrenheit imbibition under aerobic conditions. Pretty good seedling uniformity there, but that lot had tested a 96 warm, and I like to say, you know, in corn and sweet corn, the warm pulls everything up. And so we really have a 96 warm and an 80 cold, which is a pretty good lot of sweet corn. This is a pretty stressful test for sweet corn. All right, so now we've brought in a third test here. It's the accelerated aging on sweet corn. So we kept our sand germs, so the scores in the back are the sand germs. We left the cold test, the 50 Fahrenheit cold test score here on the front, just for reference, and then we want to look at the accelerated aging. So what the lab did is they commonly plant on these larger trays 2 samples. So what we've done here, so this sample here is represented on the back half of this tray. You can sort of see the leaf style differences, the morphological differences. This really represents that. The front represents the second sample. So anyway, the accelerated aging, not quite the discrimination of the 50 Fahrenheit cold test, but something very interesting at the end here. So we got a 64 plus 4 slow on this. You see a little bit of saprophyte coming in here, but a 68 accelerated aging is a decent score for sweet corn. The front rep here, which is our strongest lot of sweet corn, it had the strongest warm and the strongest cold, comes in with, in essence, a 70% accelerated aging. So a different type of stress and 70%. So I think what you're going to see here on 4 of these lots, the accelerated aging didn't really discriminate much, but on the last lot it did. So on the next ones here, we had our 56 cold and 58 cold. So we end up with a 68 AA here and a 74 over here. So our strongest AA happened to be on this 93 lot with a 58 cold. But the most interesting thing is this last tray. And what we see here is this is our 90% warm lot with a lot of rhizopus, had a 57 tray cold on a 50 Fahrenheit cold, but comes in at a 47 accelerated aging. That loss of sugars represented by the saprophyte is really showing up in the accelerated aging. All right, so we've shown you a few things. Now we wanted to look at the concept here of creating a indexing system for SH2 sweet corn. So what we did on those 5 samples, we put in some response variables, and in the sand germination that we looked at, we get the rhizopus mycelium rating here, and we get the strong normals. In the 50 Fahrenheit cold, we look at the strong normals. AA, we look at strong normals. And then bulk EC, we look at the microsiemens per centimeter per gram. And then we have 3 examples of quality indexes here. And down here, you develop an equation. So we're using, from the sand germ, strong normals, plus we do this sort of conversion of the rhizopus mycelium rating. We take 100 is a great number in an index, and we subtract the amount of rhizopus from the rating. So you see here you get a 95. So no rhizopus is supposedly showing no sugar leakage. Down here, when you have a lot of rhizopus, then we're showing a lot of sugar leakage. So then in putting the 60 in here, we only get a rating of 40, so it decreases our overall index. And then the 50 Fahrenheit cold strongs, and then we divide the works by 30, and we get these index values here, you can see. So this value here, the 8.9, we're trying to use the 1 to 10 scale, just because most people, when you say 10, they think that that's the best and 1's the worst. So we like the 1 to 10 scale. So an 8.9 is pretty darn good. And when you look at it, it has a 93 warm, which is very good. It only has 5% rhizopus, which we think is very good. Had a 78% strong cold, which we think is good. And so anyway, it gives you that 8.9. Where the one at the lowest range here, it had the most rhizopus, a lower warm, and a lower cold. So all tending or trending lower. So a 5.8, not quite the strength that we'd like to see. And the other three basically are the same. When we go to the inbred index 3, or the quality, I should say quality, it's not inbred, a quality index of 3, we keep the strong normals, we keep the Risepus, we keep the 50 Fahrenheit strongs, but we add in the accelerated aging strongs. So we now have 4 response variables dividing by 40 for that 1 to 10 scale. And you know, the question is, this costs more money to do than this, so do we gain anything? You know, and what we see with that 4th variable in there, it does reduce the index from about 0.4, 0.6, 0.3, 0.2, 0.4. So the rankings of these seed lots really didn't change greatly. It just said that really good one is not quite as strong. That probably had the biggest impact because it had a 64 AA, where its cold was 78, clearly stronger than the others, and the warm was clearly stronger. So it dropped it down. It still ranks as the best of the seed lots, and the worst of these 5 still ranks the worst. So adding AA to these response variables didn't necessarily change our conclusions. So, I mean, part of the reason we're going through this exercise is to see if we change our conclusions. And the 4th is when we use bulk EC. So on bulk EC, we have to do some manipulation or conversion of the data, and we spent a little time looking at this. In bulk EC, we think 65 is acceptable. You know, 30 is excellent, but 65 is acceptable. So we said 65 is 80%. That's acceptable. So then we ended up using a denominator of 3, dividing the actual microsiemens per centigram by 3, then subtracting it from 100. So that's how we handled bulk EC in the equation. So we retain the 3 originals of Q1, then we add bulk EC in here, and what we see here is that we're still ranking number 1 here. We moved back up, basically, from, you know, compared to the quality index 3, we moved back up closer to QA1, and but the best is still the best, and the worst is still the worst index. So what we're trying to show here, if we were to develop a standard index for SH2 sweet corn, we'd like to do that at the lowest cost. And it's still looking like, you know, this equation right here might still be the best. We want to look at 50 Fahrenheit sat cold a little more, but I'm not sure that would replace the 50 cold, but that's a possibility for us to look at. Well, anyway, that's the concept of indexing for SH2 sweet corn. Appreciate you bearing with me through this little bit of a table and these equations. But that's what we're looking for, is seed companies to partner with and working on this SH2 index. So if you're interested, let us know. Thanks for your time.